Right, let's just dive straight into this explainer on network coding. Honestly, it's a technique that's absolutely revolutionizing how we handle data transmission in complex computer networks. I mean, if you've ever found yourself wondering how on earth we're going to handle the massive influx of data in our modern world, well, you are definitely in the right place. So here's a question for you. Why does your internet still lag when you literally have a gigabit connection? It's super interesting, right? Because despite having these blazing fast connections in theory, we still end up with frozen video screens and super slow load times. And why is that? Well, it mostly comes down to how traditional networks handle traffic. They are just incredibly prone to buffer bloat and congestion. To understand how we actually fix this, let's look at our roadmap. We're going to cover 1, the network bottleneck, 2, routing versus coding, 3, the butterfly network, 4, decoding the schemes, 5, error correction differences, and finally, 6, real-world applications. Let's jump into section 1, the network bottleneck. Check out the data path going on here. Routers and switches operate in what we basically call a store and forward way. This literally means they receive a packet, stick it into a buffer, and then send it out sequentially, one by one. But if way too much bandwidth is used, those buffers just completely fill up, and that adds severe latency and inevitably leads to dropped packets. Now, obviously, in a totally perfect communication network with just one user, this store and forward method works flawlessly, no issues at all. But in the real world, we have massive competition for wireless bandwidths. I mean, your devices, your neighbor's devices, literally everyone is fighting for a slice of the exact same pie. So we desperately need a better way to actually scale our interconnected systems. Moving on to section 2, routing versus coding. Okay, so here's the major paradigm shift. Instead of traditional routing, where we cache and send packets one after another, kind of like cars waiting in line at a toll booth, network coding uses a compute and transmit model. The algorithms literally merge the messages using algebraic operations right at the intermediate nodes, and doing this drastically reduces the total number of transmissions we actually need. Let's look at section 3, the butterfly network. Take a really close look at this classic model. We've got sources 1 and 2, and they're trying to send messages A and B down to the sync nodes at the very bottom. Now, if these nodes could only route traditionally, that central link right between nodes 3 and 4, it would become a massive bottleneck. It can only carry message A or message B in a single time slot. It can never carry both simultaneously. But watch what happens when we actually apply network coding here. By using a really simple linear code, node 3 transmits the sum of the messages, literally A plus B, straight down that central link. Now, node 5 receives A from the left and A plus B from the center. And guess what? It simply subtracts A to algebraically decode B. So both destination nodes get enough information to decode their missing packets at the exact same time. It completely solves the bottleneck. Pretty amazing, right? And this exact same principle extends beautifully to wireless environments too. In wireless, transmissions from a single source can hit multiple nodes all at once, which you can see represented here by hyperarcs instead of your standard simple directional lines. So because of the broadcast nature of wireless, network coding actually becomes even more efficient. Up next is section 4, decoding the schemes. So we've got several fascinating approaches to look at here. Random linear network coding, or RLNC, is incredibly powerful. It uses random coefficients from a Gala field, but as you can see in its challenges, it requires pretty complex Gaussian elimination to decode. That is computationally heavy, especially for tiny battery-powered devices. And honestly, that's exactly why alternatives like triangular and opportunistic coding were developed in the first place, to really bring down that processing overhead. Let's actually look a bit closer at one of those efficient alternatives, triangular network coding. Here, redundant 0 bits are selectively added to the head and the tail of packets right before they get XOR coded. This creates a triangular pattern, which is great because it allows the receiver to use simple back substitution to decode everything, rather than relying on heavy mathematical elimination. So it basically gives us the performance of linear coding, but at just a fraction of the computational cost. Moving to section 5, error correction differences. Just look at the comparison here. Standard LDPC codes, like the ones used in your home Wi-Fi, are strictly for point-to-point links. They add parity bits at the source and basically just ignore the rest of the network structure entirely. But network coding, which is C on the right, actively utilizes those intermediate nodes. It actually re-encodes the data on the fly as it travels through the network. This is a massive distinction because complex networks have highly variable link qualities. I mean, some links are great, some are absolutely terrible. Standard error correction really struggles to adapt globally. But network coding, it completely abstracts those link errors. The receiver honestly doesn't care which specific packet was lost. It just needs any sufficient number of linearly independent packets to recover the original data. So it totally bypasses the massive inefficiencies of older systems that constantly have to pause and wait for acknowledgement receipts.
Finally, Section 6, Real-World Applications.
Okay, so let's look at peer-to-peer networks like BitTorrent. Traditionally, peers really struggle to find the so-called rarest block of a file to download. But when you introduce network coding, because all the blocks are mathematically mixed together, every single coded block becomes equally useful to any peer on the network. It completely eliminates that information bottleneck and just drastically speeds up file downloading times. A real game changer.
Furthermore, we're seeing this a lot in wireless sensor and mesh networks. Coding basically allows data streams to flow back and forth across intermediate hops essentially for free. The nodes don't even need to explicitly identify complex routing graphs, because the randomly mixed packets just naturally find their way to the destination all on their own.
And this quote right here perfectly summarizes our key takeaway from today. By shifting our perspective, by treating data as actual algebraic variables rather than just physical cargo passing through a tube, we vastly increase the throughput, the efficiency, and the fault tolerance of our distributed systems. Which really leaves us with a fascinating thought to ponder. As billions of new IoT devices come online over the next decade, creating just unfathomable amounts of traffic, is algebraic packet mixing going to be the only way our global infrastructure survives? Honestly, it's entirely possible that traditional store and forward routing will just become a relic of the past. Anyway, thanks for joining me on this explainer, and keep questioning how our world connects.